today we're going to start putting this concept of area with this concept of integration. Okay, so far, we've been approximating area. It hasn't been exact, right? We've been using rectangles and trapezoids. Today we're going to stick with our rectangles, okay? Because those are easier to find, right? So what happens when we add more and more rectangles? What happens to our approximation? It gets more accurate, right? So basically, we need to add up more rectangles, if you will, infinitely more rectangles. Okay? Do you see maybe where this is going?
Yes, I do.
Hello.
School envelopes by chance?
I could make them.
Are you folks doing fashion school envelopes? Could be better. It's embarrassing.
Especially your mom.
Oh.
Jimmy's all good.
Yeah, one more. No, that's
Yeah, Jimmy, you did that a little too good.
Oh, Jimmy.
Only Jimmy's shameless.
Jimmy, I don't even know what to say. Other than
Too well.
you look too good. That's really all I
No,
can
his
say.
idea was genius.
So-
No one would be able to take his eyes off of me.
Oh.
Freaking genius.
So
Right here.
I'm almost embarrassed to say this, but I didn't realize you had a nice pair of legs that you had.
I would just like to say, though,
Recorded.
this is being recorded, but the MCs didn't even ask if the students want line dance.
Yeah, no, I didn't mean to.
You guys are very.
Well, cousin's now.
What do you
A little
do?
slow.
What?
A little slow, cousin now.
Oh.
You're competitive.
Jimmy's got the energy in the house.
Okay, so this is what's going to happen. Okay, first of all, how do we find how do we do the rectangles? We find delta x, right, and that's our width,
Multiplied by the function value.
multiplied by the function value for our height. So, if we take delta x times our function value, where we have n rectangles, but we take the limit as n goes to infinity, so we are summing up an infinite number of infinitely small rectangles, we'll get the exact area.
Literally the exact.
Literally the exact.
Are you sure? Is this one so small, like so?
Infinitesimally. Nice word.
What is XK? Oh, I see.
Okay, that's for each of our infinitely small changes in x.
But if there's infinitely small, that means it's infinitely approaching zero, which means eventually zero.
No, because we're adding up all of those numbers.
But if they're
Okay.
infinitely small,
So, here is, I'm changing.
Well, no.
Okay.
I'll wait
What are you gonna multiply up on the area?
I'm going to tell you what this data means.
Anything.
When we take the limit of these sums, what we're doing is we are finding the definite integral of a function from A to B. Did you say that?
it's agreeable. That's what integral is short for.
So this represents the exact area under the curve. Now, I'm going to show you a couple properties of these integrals, and they're going to be similar to things that we have seen before. But we're going to really focus on the summation, the limit of the summation, because we need to know how that works before I can tell you how to actually perform definite integration. Okay? Yes.
What's,
B and A for?
That's where we start our interval and end our interval. So we begin at A, we
is the
stop at,
beginning.
A is the beginning, B is the end.
Shouldn't, is A on bottom and or should it be on top?
A is on bottom. So from start to finish.
Just like it's on, it's like bottom, it's like.
Yes, yes. Okay, so we're gonna talk about a couple properties just so we, understand the notation, and then we'll come back to this concept, okay? So first property, if we integrate from A to A, since this is representing area, if we start and stop, we don't go anywhere, the integral is 0. This next property is something that we're going to talk about more on Monday, but we'll write it down. The integral from B to A is the opposite from the integral from A to B. Okay. B to A, okay, those are out of order, so we're moving backwards, basically. And that's something we're going to talk about on Monday. Okay? So, yes. If we take the integral from A to C and add it to the integral from C to B, we're really just taking the integral from A to B. Does that make sense?
Like,
Right, I know that some of this feels like common sense, but we need to talk about it just to, make sure that, okay, yeah, that makes sense, we'll move on.
In this case, I'm guessing B is outside of.
Yeah. Okay, and then these last two we talked about with indefinite integrals. Okay, if we're adding two functions inside, we can split it apart into two integrals. That's going to be something important for today. And then the same thing here. If there's a constant inside, we can move it to the front. Okay, so we're going to go through some limits of summations, and we're going to notice some patterns, okay? So you know how when we had summations, I taught you those shortcuts. If you had a summation of n, of k, from 1 to n, I taught you what the shortcut was, right? So we're going to go through those, but with some limits, so you can see what happens when we take the limit of these summations, okay? You're going to see some patterns. And it's a nice chance to review limits, right? Yeah, you're all excited. Okay, first one. So we have 1 over n times the summation from k to n of 1. You guys did awesome on yesterday's quiz. What is the summation from 1 to n of 1? It's just in it, right? Right, okay? So what's the limit as n approaches infinity of n over n?
Wait, could you just cancel out the ends in the first place and just have equal one?
Yes. N over n is 1. The limit towards infinity of 1 is 1.
One. I'm one.
Oh, you were thinking aloud. Okay. Next one.
We were actually talking.
What should be one of like n squared? Is that always going to be there when we do these?
It's possible. The limit as n approaches infinity of 1 over n squared times, what's the summation from 1 to n of k?
N times n plus 1. Can we distribute and cancel out the n squares? Oh, okay.
Okay, let's think about this. We have n squared plus n over 2n squared. We can't cancel out the n squares. But we have a rational expression.
Cancel out the n.
Yeah. Take out.
If you take out the n, then you can.
True, true. Okay, so you would rather me write this as
Just leave that as n.
n plus 1 over 2n. That's what you're saying.
Two squared.
No. Because this n cancels with
Oh,
this
yeah.
guy.
Oh,
Yeah, okay. So what's that limit? It's a rational function.
infinity over infinity. So you have to take the derivative of
Uh-huh, okay. Which is?
that. 1
Over?
1.
Okay, what's the derivative of the numerator? We're using L'Hopital's rule. Over the derivative of the denominator? 2. You can also think about where the horizontal asymptote is, because we're going towards infinity of a rational function. Coefficient is 1 over 2. Okay. All right, next one. We have 4 of these we're going through. Okay, so next time you see this, 1 over n squared times n plus 1 over 2, you're going to know that it's going to be 1/2. Okay, we've already done the math. Our next one.
Oh, it's going to be one.
We have 1 over n cubed times, what's our shortcut for the sum from 1 to n of k squared?
And
And
times n plus 1 over 6.
Why did it 6?
Huh?
Why did it 6?
That's the rule.
That's proving.
Not today, sir. Not today. So, like we did before, we can cancel out this n with one of these, right?
It's like you would another 2.
Well, it was a 3.
Oh, 3.
Yeah. So then we have 6n and n squared in the denominator, 2n squared plus 3n plus 1 in the numerator.
We have to. Well, the n is the same, so 1/3.
Okay? Good. We have a rational function where the degrees are the same, so towards infinity we can just look at the coefficients, 2 over 6 or 1/3. Or you can do L'Hopital's rule twice and get 1/3.
I'm guessing that's going to be 1/4.
You think so?
Wow.
Who's with Aaron?
What's that?
I'm with Aaron.
I think the next one's gonna be 1/4.
Okay, write it down. We'll see what happens.
Oh, so you,
I'll probably be wrong.
Yeah, I really hope you're wrong.
You think this is what?
Okay. So we have the limit as n approaches infinity of 1 over n to the 4th times, what is our k squared?
N times n plus
Or k
1
cubed, sorry.
N times n plus 1 divided by 2 squared. So
So we have 1 over n to the 4th times n squared times n plus 1 squared over 4 is basically what's happening, right? Does that make sense what I did with the squares?
It's distributed, yeah.
Mm-hmm.
Not too many squares, so.
What with these?
I
Okay. So these two ends cancel out with 2 of those. Do you agree? Okay. So we really have the limit as n approaches infinity of n squared plus 2n plus 1 over 4n squared.
And it's 1, 4.
What? Crazy.
Good job. So if we do 5, it's gonna be 1/3.
Now doing that interesting.
Would you have to split up like 2K squared? And then.
We would need the shortcut for k to the 4th. Okay. All right, so when you see this, you know the limit's going to be 1/4. Okay, you don't have to do all of that calculus again. Okay? Okay, I do not want you to write anything down from this next slide. We're going to talk through what's happening. Okay? I'm going to use some math words. Okay? So what we're doing is we're doing Riemann sums. Okay? We have an interval, A to B, right? What we're going to do is we're going to partition the interval. What does partition mean? Okay, cut it into parts. Okay? So from A to B, we're going to break it up into all of these teeny tiny infinitesimally small subintervals, pieces. Yes. Okay? So the width of these little pieces is going to be delta x I. Okay, so we're going to have all these little itty bitty delta x's. Okay? And then C is any point in that interval. Okay? So we're going to take points in that interval and plug it in, right, to get our height of the rectangles times the width. Okay? And then when we take the limit as n approaches infinity, so we're taking n rectangles and we're getting more and more and more and more and more and more and more until infinity, that becomes our exact area. Okay? So I'm going to go back to this slide here. You already have written this down. Now, since we have all of these shortcuts with k equals 1 to n for our sums, it is going to be beneficial to us to use the right hand rectangles, yes, rule for this Riemann sum. Okay? Now, if we have here's A, here's B, right? Our right-hand rule means this is what our rectangles look like, right? Okay? So do we start by plugging in A to our function for our first height?
No.
We do not. We start by plugging in what number?
A plus delta x.
A plus delta x. Okay? Very nice. So, each of these values that we're going to plug in to find these infinitely many heights is going to be A plus K times delta. Yes, you should write that down. It is important. Yes, I am.
But that's only for right-hand limits or just?
Well, that's all we're going to do with Riemann sums, because all of our shortcuts for these summations work out with going from 1 to n, okay? And so with a right-hand sum, you know, the last number we plug in is that b, okay? So that's okay.
But if there's infinitely small pieces, wouldn't there still be more area on the
Because they're basically small enough to where they're not even, like you're saying, that over approximation is what you're saying. Yeah, they're so small, they're not going over. If you want to imagine that, yes. Okay. All right. So this is the first example we're going to do. I want to find the area under y equals x squared from 0 to 5. Okay. So our interval, so you can write it down, is 0 to 5.
How many?
Infinitely many rectangles. I know, we're in that mindset of how many do I need, but infinitely many. We'll sum them all together. All right, so first of all, the area under this curve, we write the integral from 0 to 5 of x squared dx. This is what we are finding. Okay. So, let's talk about these infinitely small rectangles. We still need to find delta x. How do we find delta x? In general, b minus a over n. So in this case, 5 minus 0 over n. Remember, we're eventually going to take the limit as n goes to infinity, so we're just going to keep n. All right? Now,
Now do we put on the outside?
well, now we need to know what x sub k is.
Wouldn't it be,
So what's our a?
wouldn't it just be k delta x?
Mm-hmm. So since we begin at 0, that actually makes this example kind of nice, which is why I'm starting with this example, okay? And then what did you say, Jimmy? You said,
Plus k delta x or k 5 n.
so plus k times 5 over n, yes. So I'm going to write it as 5 over nk. That'll look nicer. So what we're going to do, the integral from 0 to 5 of x squared dx means we're taking the limit as n approaches infinity of the sum from k equals 1 to n of, how do we find our rectangles? Okay, delta x times f of x, right? So here, whatever we find here, this is what we need to plug into our function. So 5 over nk is getting plugged into our function. So 5 over nk squared. That's each of our function heights times delta x.
What's the square? Because of that square.
Because our function is x squared. So we're plugging it in to get our function, to get our heights times delta x. Thank you. Yes.
What's the first of 0 in the,
That is a. We have to think about where we start.
so where would that go? If it wasn't 0 because of 2, where would that fit?
So if that was 2, then this would be 2 plus 5 over nk being squared.
Sorry, where is the second 5 over n?
That's
Okay.
times delta x.
Let me do this.
So is that
So f of x means we're plugging x into our function. So 5 over nk squared, that's our function, times delta x, which is right here, 5 over n. Okay, so now let's take this do we really have? How can we rewrite that?
Over and outside.
25 over n, 25 over n, 25 k squared over n squared times 5 over n. So
Yes. So basically we have 5 cubed over n cubed times k. This is 5 squared times 5, and then this is, and this is k squared.
Yeah.
Thank you. Thank you. Okay. So now we get to evaluate this limit, right? So let's first of all work on our summation. Okay. This is basically 125 over n cubed times what's the sum from 1 to n of k squared?
Wait, what?
N times n plus 1 times 2 plus n, 2 plus 1 over 2.
Oh, okay.
Okay. So this is the summation now.
So 125
Try again. Okay. If it helps, do we want to bring the 125 outside? Would that be helpful?
Yeah.
Like we could do this.
so it's 125 over 3 or 25?
We can do that. We can take the 125 out, and so we have that limit. Now we've already done this limit, haven't we? This was already 1/3. So we have 125 times 1/3, or 125 thirds. That is what? You said half. You did right. Okay, then yes, that was right.
Wait, so what do you do with the 1 over n?
Remember that goes with this to get all of this has a limit of 1/3. Because we have 2n cubed, something, over 6n cubed. And that's how we get the 1/3. So our exact area from 0 to 5 under y equals x squared is 125 thirds.
Can you try to calculate that? Or
What would happen if, how far would we be off if we did like 5 rectangles and
It depends on the function. I mean, you're going to be close, but this is exact area. Exact. Yes.
What is the integral again?
Well, this is what we did to evaluate the integral. Okay? That makes sense? Okay. No? What is it? Okay, sorry.
I'll just go on to the next one for you guys.
Okay. We'll do another one. Okay, so our interval is, what did you say? Okay, so what we're finding is the integral from -2 to 2 of 4 minus x squared. Okay, so the first thing we need to find is delta x. Delta x. B minus a over n. What is delta x?
4 over n.
Okay. Now we need to find x sub k. X sub k, a plus 4 over n times k. Delta x times k. approaches infinity of the sum, okay, n, of f of x of k, delta x. Those are our rectangles. Delta x is our width, f of x is our height. So how do we get f of x? Okay.
It's 4 minus, or xk squared times delta x.
That's all it worked. F of x times delta x. This should be fun. Okay, so let's do this. We have 4 minus. When we take negative 2 plus 4 over nk, the quantity squared, what do we get? The binomial squared, so a binomial times a binomial, you're going to have to FOIL. Four. Minus,
Minus 8 and
and that happens
k.
So 16 nk.
twice. So minus 16 over nk plus
And 14 k squared. Well, 16 over n squared.
Forget the negative 16.
because we have negative 2 times 4 over nk
Is negative.
twice. So we have negative 8 over nk twice.
Okay, then how'd you get to?
Because that would
then
be.
You added that, okay, I thought it meant that.
So now we have 4 minus 4,
Zero.
okay? And then we have minus a negative 16 over nk, so that becomes positive. And then we have minus a positive, so that becomes minus 16 over n squared, k squared.
Factor out of
Well, we're gonna want to multiply that 4 over n to both of them, right?
we have to continue to write limit as a D problem.
Until you take the limit, you need to write limit. So we have 64 over n squared k minus 64 over n cubed k squared. Okay. Now we can break this up into 2 separate limits if you want to, right? That's possible. Okay, so let's think about this. Let's take 64 out. And we have the limit as n approaches infinity of 1 over n squared times, what's the sum from 1 to n of k?
N plus 1 solutions.
Minus, we can take out the 64 times the limit as n approaches infinity. We have 1 over n cubed. What's the sum from 1 to n of k squared?
Hello, Pavilion of the South. It's time to rise from your seats for today's Pledge of Allegiance.
Okay, we'll say the pledge and we'll finish this. I know we had enough.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Thank you very much. It's now time for your Titan Duty Bulletin, January
Okay, this.
22nd. Information. Titantown closed at 11:45 today, so sorry if you had to go to Titantown, you'll have to wait for Monday. Students, here at Killeen La Vista South High School, we strive for excellence in all things. Every spring, 11th graders across the state take a series of NISA exams that are designed by Nebraska's Department of Education to measure their level of achievement in the areas of writing, reading, math, and science. Reminder, Papillion La Vista South will be operating on a block schedule on Tuesday, January 26th, and Wednesday, January 27th. Due to the NISA testing, the times for the start and end of the school day will remain unchanged. Please see posted block schedules in the hallways or ask a teacher if you have any questions. Cheer! Attention anyone interested in trying out for PLS Cheer for the 2016-2017 school year. There will be a mandatory parent meeting on Wednesday, January 27th at 6:30 p.m. in the PLS cafeteria. We will be giving out information regarding tryouts and important dates for next year. Drama in ITS. There will be a drama club in ITS meeting Tuesday, January 26th at 7:15 a.m. in the theater. All members should attend. See you there.